Signals and Systems, CT Fourier Transforms, Problems, Part 1, Series on Signals and Systems, Lecture number 3.14. Ctft stands for Continuous Time Fourier Transform. It is relevant to continuous time signals. To transform these signals into frequency domain. When the signal is in a frequency domain, it becomes quite easy to see the frequency content of the signal. In this session, we do some problems which are set around CTFTs. Mostly, these problems use the defining relation of the transform and also property, time differentiation property of these transforms. Now, let us move further to solve the problems. Before going to the actual solution procedures, let us recollect the defining relation of CTFT transforms. The Fourier transform, it is indicated by f of omega. For a CT, continuous time, non-periodic signal f of t, small f of t. Small f indicates that it is in time domain. Capital F indicates that it is in frequency domain. Of course, in addition to that, t is there as an independent variable. In fact, it tells that small f of t is in time domain. Omega is there along with capital F. It tells that capital F depends upon frequency. Independent variable is frequency. Right now, Fourier transform of f of t, f of omega, by definition it is integral minus infinity to plus infinity f of t e power minus j omega t dt. This relation gives frequency domain signal from time domain signal. Another relation is also given. This relation gives time domain signal from frequency domain signal. F of t is equal to 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t d omega. First one is called analysis equation. This is also forward transform. Forward transform is one which converts signal from time domain to frequency domain, whereas reverse transform is one which converts signal from frequency to time domain. Reverse transform is also called synthesis equation. The frequency domain signal f of omega is in general a complex quantity. It is function of angular frequency omega. There is a name for this, technical name. It is called spectral density function. It is better to have these defining relations of CTFT transform in mind while going to solve the problems. Problem 1. Evaluate the Fourier transform of function f of t given. Here is a signal given. It is in time domain. It's in a graphical form, a waveform. It exists from -2 to 2. After t equal to 2, it is 0. Before t equal to -2, it is 0. It is reaching a maximum value of plus a in positive direction, minus a in the negative direction. Ft is given. We are asked to find out f omega or f of omega. To get the answer, we use the defining relation. For that, what we need to do is first we have to express this graphical signal into analytical signal, or signal in graphical form into signal in analytical form. The signal can be expressed as f of t equal to at by 2. T is in between -2 to +2. So this is analytical expression corresponding to the signal given in graphical form. F of omega is integral -infinity to +infinity f of t power minus j omega t dt. This is defining relation. F of t is at by 2. Substitution at by 2 for f of t and limits instead of -infinity to +infinity, -2 to 2. These limits are sufficient. Now integration and a little bit of manipulation gives us f of omega as 2 by omega square 2 j omega cos 2 omega minus j sin 2 omega. Another problem 2. Evaluate the Fourier transform of function f of t given. F of t is shown here. Expression for this signal, analytical expression, is a cos t. F of t is a cos t, and it exists only in between -pi by 2 to pi by 2. Beyond pi by 2 it is 0, below pi by 2 also it is, prior to -pi by 2 also it is 0. So f of t is a cos t minus pi by 2, pi by 2. This is the range. Here also, in this case also, we use the defining relation to find the transform. To find the transform for the given signal, one can use the defining relation of Ctft Fourier transform. F of omega is integral -infinity to +infinity f of t e power minus j omega t dt. This is defining relation. Appropriate limits in the present case become -pi by 2 to +pi by 2 over integral sign. F of t is k a cos t. Of course, e power minus j omega t is part of the definition dt. Integration and substitution of the limits and a little bit of manipulation gives us the answer as 2a cos pi omega by 2 by 1 minus omega square. This is f of omega for the given signal, Fourier transform of the signal a cos t. Another problem 3. Evaluate the Fourier transform of function f of t given. Notice the waveform consists of several lines. Line 1, line 2, line 3, line 4. Of course, it is symmetric around the vertical axis. The signal spread is from -2 to 2. Beyond 2 and before -2 it is 0. This problem can be solved using the defining relations of Ctft, but there is a much simpler, easy method. This method uses a property of Ctft, that is time differentiation property. According to this property, differentiation in time domain corresponds to multiplication with j omega in frequency domain. We use that property in solving this problem. Solution. Differentiation of the given signal graphically results in 4 pulses. One from t minus 2 to 1.5 with amplitude minus a. Here, one pulse like this, minus a amplitude. Another pulse from t minus 1.5 to 0 with amplitude a. So like another pulse from t equal to 0 to 1.5 with amplitude minus a. Last one from t equal to 1.5 to 2 with amplitude a. Like this. Pulse 1, pulse 2, pulse 3, pulse 4. Differentiation again results in 5 impulses. One at t equal to -2 with the strength -a, another one at t equal to -1.5 with the strength 2a, third one at t equal to 0 with the strength -2a, fourth one at t equal to 1.5 with the strength 2a, and last one at t equal to 2 with the strength a. So here one impulse, here another impulse, here another impulse, here another impulse, here another impulse. 5 impulses. And now one can write down the expressions and sum them to get d square f by dt square. Pulse at t equal to -2, pulse at t equal to -1.5, pulse at t equal to 0, pulse t equal to 1.5, pulse at t equal to 2. When I say pulse here in this expression, I mean impulses. Impulse. So before going further, let me mention the fact that these are impulses which we got when we differentiated the given signal twice. So d square f by dt square is sum of these 5 pulses. Now apply Fourier transform, continuous time Fourier transform, both sides. Fourier transform of d square f by dt square is j omega whole square f of omega. Fourier transform of these 5 impulses, they give us minus a e power j 2 omega plus 2 a e power j 1.5 omega minus 2a plus 2 a e power minus j 1.5 omega minus a e power minus j 2 omega. By transferring j omega square to right hand side, we get f of omega equal to 2a by omega square cos 2 omega minus 2 cos 1.5 omega plus 1. This result is after some manipulation. Another problem. Evaluate the Fourier transform of function f of t. Here is the signal. It is in time domain, but it is in graphical form. This problem also can be solved in 2 ways. One way is by using defining relations of Ctft, but the simpler way is with the help of time differentiation property. We do the second way. Differentiation of the given signal graphically results in 2 pulses, -2 to 0, 1 pulse, 0 to 1, another pulse. First one is positive pulse, second one is negative. One from t equal to -2 to 0 with amplitude a by 2, another from t equal to 0 to 1 with amplitude -a. Differentiation again results in 3 impulses. One at t equal to -2 with the strength a by 2, another one at t equal to 0 with the strength -3a by 2, and the last one at t equal to 1 with the strength of a. So differentiating these pulses results in 3 impulses. One impulse here at t equal to -2, it is positive. Another impulse at t equal to 0, it is negative. Another impulse at t equal to 1, it is positive. So therefore, we have differentiated the signal twice. So d square f by dt square, it is equal to half a delta t plus 2 minus 3 by 2 a delta of t plus a delta of t minus 1. Delta means impulse function. 3 impulses. One impulse at t equal to -2, another at t equal to 0, last one at t equal to 1. Now apply time differentiation theorem property. Fourier transform of d square f by dt square is j omega whole square f of omega. Now we can apply Fourier transform to the 3 impulses. They give half a e power j 2 omega minus 3 by 2 a plus a delta e power minus j omega. One can take j omega to the other side, a little bit of manipulation, then gives f of omega as minus a by omega square half e power j2 omega minus 3 by 2 plus delta. Here delta need not be there. E power minus j omega. Another problem, evaluate the Fourier transform of function f of t. Here also we use time differentiation property. Solution. Differentiation of the given signal once results a set of 3 impulses at t equal to minus tau, t equal to 0, t equal to tau with the strength a, minus 2a and a respectively. Differentiation gives one impulse here, another impulse here, the third one here. So df by dt is equal to a delta t plus tau, impulse at t equal to minus tau, minus 2 delta of t, impulse at t equal to 0, plus delta t minus tau, impulse at t equal to tau. Apply transform on both sides. Left side we get j omega f of omega, right side it is a e power j omega tau minus 2 plus e power minus j omega tau. After taking j omega to the right side and doing a little bit of manipulation, it gives f of omega as 2a by j omega cos omega tau minus 1. Another problem, this problem is also based on time differentiation property. Differentiation of the above signal twice results in a set of 4 impulses. One impulse here, another impulse here, another impulse at t equal to a, last one at b. When we differentiate f of t twice, it becomes d square f by dt square. It results in 4 impulses. One can write down the expressions for these impulses. So d square f by dt square equal to a by b minus a delta of t plus b minus delta of t plus a minus delta of t minus a plus delta of t minus b. Using time differentiation property, one can write Fourier transform. One can apply Fourier transform on both sides of the signal. Now apply time differentiation theorem. It gives us left side j omega whole square f of omega, right side it becomes a by b minus a e power j omega b minus e power j omega a minus e power minus j omega a plus e power minus j omega b. After taking j omega square to the right side and doing a little bit of manipulation, one can get f of omega as 2a by b minus a whole square multiplied by cos a omega minus cos b omega. The solution to this problem can also be found using defining relation of Ctft, but it involves integration, lot of integration and consequent complications. Another problem, 7th problem, evaluate the Fourier transform of a function f of t given. It is a triangle function. Its spread is from minus tau by 2 to tau by 2 with the peak value equal to a. Solution. Differentiation of the above signal twice results in a set of 3 impulses. 2 of strength 2a by tau at t equal to minus tau by 2 and tau by 2. One with a strength of minus 4a by tau at t equal to 0. So d square f by dt square becomes equal to 2a by tau delta t plus tau by 2 plus delta t minus tau by 2. This is superfluous, minus 2 delta of t. Now apply Fourier transform both sides and use time differentiation property. It results j omega whole square f of omega on left side, right side it is equal to 2a by tau e power j omega tau by 2 plus e power minus j omega tau by 2 minus 2. J omega square can be carried to the right side and right hand side can be manipulated to get f of omega as a tau by 2 sample function square omega tau by 4. With this we come to the end of this session. Here we solved several problems set around Ctft. Mainly these problems, their solutions, they are about defining relation of Ctft and also one important property of the Ctft, that is time differentiation property. Hope this session is useful to you. We meet again soon in another session with a new topic.